The last week has been pretty rough on me. And it took me 2 hours to get home yesterday. So it looks like it's continuing today. Okay. Maybe we can have a little bit better luck than I've been having. Um, so, um, so I need no introduction, so we don't have to go through that. And given that we had a cancellation due to the COVID, which is around, I decided to step in. And so I'm going to be talking about the overview of the future E plus and minus colliders from the standpoint of the problem of the theoretical precision of the corresponding luminosity. And this is a work that has started with Yadok and Placzek and Schipek and Yost. You might say it even started already in 1988, I would say. 88 was when we made our first effort on this type of problem. It was, of course, for a different machine. I mean, it was for the machines in SLAC at the time, when SLAC used to be a high-energy physics laboratory, which it no longer is. And so let me just, let me see if this is going to work. Maybe not. It's not working. Why won't it work? It won't work. Okay. Oh, because this is not in. Somebody took the, so I have to work this over here. Somebody took it. It should be a battery for it, and it's gone, you see. This little thing here is gone. Somebody just took it. I don't know why. Sometimes we have it, sometimes we don't. See, it's just not in here. That's mine. That's mine.
What about this one?
Yeah, that could be it. Let me see. No, I don't think that's it. No, it fits in here. It looks like that, but it's just not here. Okay, simple. Now, so let me just do it this way. I want to start out talking about, talking about the future E plus and minus colliders. And you see here I have this is from Rossi, his name is there, at the meeting this summer in Bologna. And what we can see is, of course, this is all history, but he has got the future up here. This thing here needs to be, I can see myself, I can't even see what it is. So this kind of thing here, you may consider the progression of the proton machines, and that's the 100 TeV machine, which if we had, for example, the superconducting supercollider, it would be at 100 TeV, but we don't have it. And the machines I'm talking about are these lines here. So this is the Chinese version of the future E plus E minus collider. This is one at the CLIC machine at CERN. This is the FCC machine at CERN. And these are muon colliders, which I won't talk about. And so you can see that, where is the IOC? It should be up here also. I thought, why doesn't he have the IOC up here? Oh, there it is, yeah, sorry. No, that's not the IOC. It should be up here. That's very strange. One TV. He left it out. Anyway, there's an ILC as well that is similar to this CLIC, except that CLIC, as you see, can go up to where this is a 3, and ILC should be right here on the plot. It's just missing. I apologize. Now, and so those are the kind of environment in which we're working. Now, none of these machines out here, none of them have been approved or anything like that. All of them are in sort of what we call study stages, Probably the most mature one is unfortunately the one he left off. It's really not on here. I didn't notice that. The IOC, because it was really started, around the year 2000, a little bit before the year 2000, and so it could be built if some government would agree to build it. All of them are in the point now that they have their hats in hand before various governments asking for money, asking to be built.
What about the linear collider in Japan?
Yeah, this is what I was just saying. He took it off the plot. It should be normally right here, okay, right in this region here. And he took it off the plot, and I think he took it off the plot for a reason. He took it off the plot because just before he gave his talk, the Japanese government a few weeks earlier tabled the project in Japan. So they are not going to be making any decision to do that anytime soon. And maybe that's why he doesn't have it on the plot. However, we do have slides on it. So he didn't kick them out altogether. Okay. Now this one, which is my favorite one, the FCCEE, you see, this is the SSC type tunnel that they want to make on the Geneva, the lake. This is Lake Geneva here in this area. This is where the current LHC is. The Jura Mountains are there. And it's going to be almost exactly the same size as the one in Waxahachie would have been. We have 1/3 of the tunnel in Waxahachie exists, by the way, in case you don't know that. And efforts are being made to get President Biden to take advantage of that. The idea is to first put in the E+E- machine, if you get this ring, and then follow it up with a hadron machine. So 2045, 2060. So you see 22 years from now. Whereas Biden, if he wants to swing his stick, he could do something in 10 years. 2033 or so. And just take this all over if he wanted to. I mean, I'm just saying, he could. Now, this machine is CERN's future, and you see they're quite serious about it. This is this woman, Fabiola Giannotti, is the Director General of CERN, and she really has decided that they're going to pursue this in a very systematic way, with the idea that sometime soon they would take a decision so that they could have this. Now he didn't. Oh, here we go. So the study, you see, 2025, and they want it approved so they can start building it in 2030. Is what they want. Okay. And I think it goes up to, if you can see that, to 2090. So with this hadron machine. So it's the future of CERN. I just don't see how they would not do that. I don't see how. And these are the reasons why they want to do it. I won't go all the numbers, but basically you're looking at these luminosity numbers, and these are gigantic numbers of Z's, W's, Higgs. The rule is, at this kind of energy they're running at, you see, he's saying per year they get 3.5 inverse attobonds at this energy, and it turns out that a rule of thumb is that for every 5 inverse attobonds you have 1 million Higgs. And so you can have, therefore, the type of precision we had on the statistical level at LEP. If you have 4 interactions and you run this for 4 years, you would have essentially LEP-type statistics with Higgs particles. It's an incredible opportunity. I don't see how they would not do that. So that's the main thing to take away from this one. Of course, you can see that in the Z direction, they do something that's unbelievable, because that number corresponds to that if you run the program 3 or 4 years there, you have 10 to the 12, a few 10 to the 12 Zs, and that the entire LEP program had about 2 10 to the 7, so 5 orders of magnitude is what they're talking about in statistics. It's an incredible, which is why I don't see why Biden is just sitting there. Everybody says he's incompetent. He could show them that he isn't. But the Chinese have a strong program also in this regard. I want to stress that point. They want to build something that just like that 191 kilometer tunnel that I talk about here. They show, I forgot where this is, but you see all of them are, of course, buried deep on the ground, hundreds of meters below. And here's their schedule, and it's pretty aggressive. Now, they put in this international collaboration as a requirement, and that's what has killed that's why they have tabled the machine in Japan. Because, you know, and you notice that CERN is not doing that. You didn't see anywhere on that, any of their transparencies where they had a requirement for international collaboration. Similarly with the super collider, we did not have any requirement for international collaboration. This was Ronald Reagan just doing something. You know, it wasn't that if this one gives me 20% and that one gives me another 10%, then I'll do it. No, this was Ronald Reagan saying, I'm going to do that, okay? And that's what the CERN people have. This is always very bad. It's a bad thing to see. We haven't had good experience with that, okay? But the rest of it is very similar to what I showed you for CERN. With a 15-year period to run on the E plus E minus, just like with CERN. I mean, it would essentially attempt to do almost the same schedule as CERN if they can get approved. Now, their main problem right now happens to be a Nobel laureate by the name of Chen-Yin Yang, who got the Nobel Prize for discovering the theory of parity violation in the weak interactions with Professor T.D. Lee, because he has recently relocated to China, renouncing his U.S. citizenship and becoming back Chinese, and entering the high levels of advisement to the government. And he is against this machine because it costs, maybe I had the cost, did I have the cost there? Maybe I didn't. It costs similarly to the, let's see, go back. I didn't show the cost, probably not. Okay, I didn't show the cost. But these are 15 to $30 billion projects is what they are. And Dr. Yang believes that in the current China, where the majority of the population is not living like what we see. We see 400 or 500 million people living similarly to the way we live. But there's another almost 1 billion people that are not living like that. And he says it's immoral when you have that to spend $30 billion on such a project. And he is strongly against this machine, and they will never touch it as long as he's alive. He's now, what is he now, 95 or 90? He got 100 now. Okay. Now you see, he put the ILCs in the discussion, although you saw he headed off the initial plot. Here we have the idea. This has been around since the 90s. This linear collider is the SLAC invention, invented while I was out there. So you have one direction E plus, another direction E minus, and in the damping rings, all that was invented in SLAC. I mean, all of this was invented. And SLAC could not build this because, you see, they did something that you really should never do. They were jealous of the superconducting supercollider because its budgets were big, $500 million a year for construction. So they said, once the price got to be 8.3 billion, I think it was, they said that this is unacceptable as the cost of a high-energy physics accelerator. Dr. Richter, the Nobel laureate, the one who found the Psi-J particle, he himself went to DOE and testified that this was unacceptable. Well, it turns out he made an estimate for a machine like this one, and he underestimated in a big way the cost. So when the government accounting office came to do their version of the estimate, the OMB they call themselves, they had a price that was $12.5 billion. Now, given Slack's record, had he not said what he said, they would have just said, okay, you made a mistake. It's going to cost more than what. But when you spend $8 billion, why can't you spend 12? You know, I mean, what you got $1 trillion economy, a few $1 trillion is what they're taking this out of. You can't even see it, you know. So, but they use his own words against him, and they said, well, you can't have that. And so now this was supposed to be built in Japan. There you see, $5 billion, because the energy is lower than what Richter would have had. This is just to get to 500 or so. Maybe I have it up here again. Even 250. That's why it's only $5 billion. But Japan wanted international collaboration, and they did not get enough, so they have tabled this machine. But as you see, it requires 21 kilometers. Out at Slack, they would have had to put it, if you know that area, there's a bay over on the other side where Berkeley is, and then there's a valley over there, and that's where they would have put it. It's a pity that they didn't do it. This is where they were going to put it in Japan. Now I think this is showing the Tohoku, yeah. And so this region is, where's Ken? He's not here. Maybe he's online. No, Ken is here. Okay. Is this where the earth, this accident was? The tsunami thing? This is where it was. Yeah, that's why that's one of the things they were trying to use to promote it. And I really believe if they had gotten international collaboration, they would do it. But they haven't gotten it. CERN also has a linear collider project. They call it the Compact Linear Collider. And you see, for similar 20-ish kilometer size, 25, you're getting a lot higher energy. And in fact, in principle, if all of this dual accelerator type structure works, essentially they have an accelerating structure that involves two beam accelerating techniques. So they use one beam to help accelerate the other one, is how they're doing that. Anyway, it can get, in principle, 3 TeV, which is the highest E plus E minus collisions that anyone's ever said they could try to reach. And I believe they could do it. I mean, you see, it's been, here you're looking at the CDR in 2012. CDR means Critical Design Report. I mean, that means that somebody thinks they actually would be able to pass on to the next stage if they had the money, you see, project implementation plan. I mean, you know, I mean, they really, I believe them. I think they could do it if they could get funded. I don't think there's any question about that. The cost, $6 billion, I used to have to distinguish, but now the dollar is so strong I don't distinguish anymore. So I just say, let's call it $6 billion. And at 380, and then you, of course, your price goes up if you want to get to 3. You know, you're talking more money. Now that's not dead. Fabiola is not saying that that's dead. You see, he says it can easily be extended to the TeV regime. Here's is showing this two-beam accelerator idea. I don't want to spend too much time on that, but I wanted to show you where it is. You see, it's because I said it's always 20s of kilometers, and so you have to go in this way away from the along us. And this is supposedly where the current LA, that should be the LEC, I think. So they have a site. If Fabiola could give a go-ahead, they could make this machine. I don't have any question about it. Now, let me make sure I didn't miss one. FCC, EEC, EPC, CLIC, and IOC. So I have them all up here. And in this table, I'm showing, now this, you say, why did I pick 240 GeV to show you? This has to do with the European strategy. The Europeans periodically make a big strategy for the field in Europe. And they had this process, and they came up with the conclusion that the most important machine for Europe to make as the next new collider in particle physics is an E plus E minus that can make large numbers of Higgs particles. And it turns out the process involved is therefore optimal around 240 GeV, so-called Bjarkane process, where you produce Higgs and a Z together off of a Z. So you come in with E plus E minus, you get a virtual Z, and it decays into a real Z and a Higgs. Something Bjarkane, although they don't like to say it, but he wrote that down first. And this 8.5, if you translate it into what I told you that you need, you get for 5 inverse Atabarns, you get 1 million. Means that all these, means that all of them could meet that. Of course, you need, it depends a little bit of them having the right detector match, but all of them with the appropriate number of years, you see, because these are all within a factor of, let's say, 3 of each other. So it means that, okay, one of them might have to run a little longer to do it. That's all it means. Okay. So they could all meet that. And but somewhere here I have the costs, 12 to 18 for the FCCE, 7 to 12 for the others, more or less. So it's just the cost of our SSC. I mean, how can a country that is supposed to be the leading technology entity on the planet sit still and do nothing while the other large areas with the capability put in $20 billion on something as fundamental as physics? It just doesn't make any sense. We had a lot of lessons that we've learned from our previous E plus E minus days that we would like to take to this high precision era. Here I show, this is this Z region that they want to produce. These data points are what you get in the experiment, and this is what you get when you remove the high order corrections. So you use theory to get from here to there. You see, it's a non-trivial amount of correction that has to be done in order to take advantage of these large numbers of statistics. You cannot do it without theorists, but you would never know it if you look at the funding profiles. You just would never guess that. I mean, you would think that this just comes for free. Well, it doesn't, okay? It doesn't. And here's a list of all the things that they think they can get by under-supporting theorists. You know, if you compare the observables on the Z, the mass, the width, the ratio of the hadrons to leptons, the number of massless neutrinos, Weinberg's mixing angle, etc., huge factors would be required in the current theory that we have to match the errors that something like FCC or the Chinese machine or click, ISC, it doesn't matter which one you take, data would necessitate. In the case of this neutrino one, we already can see the effect because this is the formula relating the ratio of the invisible width to the visible lepton width, and it's related to the number of massless neutrinos, and which I show here. So if you have 3 of them, then you have 3 times this. This is all from theory. You see, standard model means that a theorist has calculated it. And at the end of LEP, it was determined that we have N nu equal to 2.9840 plus or minus 0.82. And the luminosity theory error, which is something that my group provides, was adding 0.046 to this error that you see here. Recently, we've been making improvements, even though they haven't paid for them yet. It's an investment. And we've reduced this 0.61 down to, this number has been reduced down to 0.37. And in this article, one of my collaborators and other people showed that this number is now known to 299.75 plus or minus 0.074, where our part of the error has, you see, been almost, well, we reduced it down to 0.028. Now, when you get to the FCCE, this needs to go further, down by a factor of 3.7. That's the requirement to take advantage of the situation, and that's one of the problems that I'm trying to talk to you a little bit about today. How do you get down to this factor of 3.7? And so this is sort of what I just showed you. You need to improve this current situation so that that 3.8 becomes a 1. That's what you need to do. And these are the contributions that one has to calculate, the so-called photonic corrections, which means you radiate photons to this order. This logarithm means that there's an enhancement whenever the photon is emitted from, as you know, from Jackson, that we were just talking about. And that people are saying they're not learning anything. From Jackson, we know that when the photon is near the charged particle, we get a logarithm of its momentum, or its energy over its mass. That's the big log that I'm talking about here. And so you have to calculate, every power of alpha then has one power of this with it. And we have control over all of them to the level I'm indicating. There's vacuum polarization, production of pairs, and other types of effects. And all those, you see, have to be improved because we want the end result to be 1 over 3.8 times what I was showing there. And so we have put this, in fact, I asked DOE to support that I do this, you see. So this is what happened to those numbers that I showed you. And I asked DOE to support me, you know, to bring that number down. See, this is the 1.0. All of this is sort of the 2018, what we knew then. And we know how to do all of that, the light pairs, ZS channel, we know that. We know how to do it down to the point that we would really have what those high statistics require, okay? So I asked DOE to support me to do this. And I got back this here, not urgent. And you see, of course, I don't like that he says that, or that they say that, but what can I say? You saw the schedule that Fabiola had. She was talking about this machine running in 2045. You know, 22 years from now. Can I say that it's urgent? I mean, it's not. It's just. I mean, at some point, you know, you get bad news, but you can't do anything about it. I mean, it's just true, right? It's not urgent. In the meantime, we're getting some competition, which is a good thing, because you don't. Of course, we're confident that what we do is correct, but it's good to have someone do a completely independent analysis and get exactly the same conclusion. And we're getting that from this group by my friend Adrian Ziegler in the Power Institute in Switzerland. And they are asserting that they can do a calculation. They call it, in the jargon, it says NNLO BABA. That means that it has up to 2 big logs and 2 powers of alpha in there, and all the terms with less logs and still the same number of powers of alpha. So it's what I said that we do. But it's done by a completely independent method from what we do. Now, the reason I put these here is because he doesn't reference these papers. So if you take my transparencies and you go find his paper, you will not find these papers. But these are the papers that tell you that he's calculated the same thing that we've calculated, except that he is supposed to have the alpha over pi squared term. That's a pure alpha over pi, no big log in it. So it's a few 10 to the minus 5 type, 10 to the minus 6 type few 10 to the minus 6 type object, well below what we're talking about. And he doesn't, for some reason, he doesn't want to tell people where those papers are. So we did some comparisons on this. I mean, because one of the most important things about your work is that you should be able to show that it's consistent with other practicing recognized experts in the subject. So this is the term I just told you that we do not have, and he's supposed to have that term. Well, there's a third Italian group, Baba Yaga. Baba Yaga means something, but don't ask me what it what it means. The Baba part is easy, that's Baba Scatterman, but this Yaga is beyond me. So if you take these 2 programs, we're both supposed to have this term, both are NNLO, they both have all the powers at order alpha squared in the calculation, all the big logs, so L squared, alpha squared, L alpha squared, and the power with just alpha squared over pi by itself. They have an agreement at the level of 0.07%, when they should agree at the level of 4 to the minus 6. So there's a 2 order of magnitude discrepancy between what they should show as an agreement and what they can actually show. In other words, when they actually put their 2 calculations on the same acceptance and same conditions and compare the results. The thing that Signer doesn't say in his abstract, I see my transparency got messed up a little bit, is he makes something called the so-called next to soft approximation. Now, if you're studying particle physics, you can learn that this is what we call Lowe's theorem from Professor Francis Lowe at MIT. He showed that any cross-section, if you take the limit in which the momentum transfer so small, you can expand it in powers of the arguments of the soft. So let's say in this case, the photon is the one that has the soft components to its 4 vector. You can expand it in powers, and he's taking the term. This is the term that's in the leading term, if you will, and he's taken 1 power less in the limit. You see, because over here I have epsilon squared, so this term really looks like 1 over epsilon, and this c squared, and the other one looks like the n plus 1 times 1 over c squared, 1 over c. So if you expand those out, you'll see that there's a term in the second part that I show as n plus 1 that has the form of k of 1 momentum, let's say of 1 charged particle, divided by k of the other. So so even though both of the k's are small, it's a ratio of small things. And he's supposed to be taking that into account. The problem is that in his exact formula, he cannot, oh, let me not go off of that so fast. In his exact formula, he's unable to not use this approximation to evaluate his cross-section, and for the reason of numerical instability. When you put in these higher-order corrections, you have the occurrence of overlapping divergences where the divergence is not just simply a question of subtracting one function. It's actually a combination of functions. And if he tries to tell the computer, and I mean he has the biggest computers in Europe, I'm talking about, if he tries to tell a computer to calculate his cross-section without this approximation, so in other words, don't use this, don't stop this, but actually use what he actually calculated, you know, which is all automated. You know, everything is automated. I mean, so he uses the computer to draw the Feynman diagrams, to put numbers on each diagram, put the diagrams together, put them into the, all of that's automated. He doesn't touch any of that with with human hands, okay? It's all automated. But if he asks that without the soft approximation, it does not give an answer because of the numerical instability. The integrations, maybe you know some of these names, the Vegases and all these integration routines that people use, they require some consistency before they tell you it's the answer. If they don't see consistency, they will just not give you an answer. You know? They don't give you an answer. He cannot compute his fully exact result. So he uses this approximation, and I have tried to convince him that maybe that is why the two of them don't really agree at 5 × 10⁻⁶, the way they should. That this numerical substitution that he made is the reason that they have this disagreement. Now, he has not agreed to that. However, he has had a chance to come and explain why it's not true. And he has not appeared so far. Now, why don't we have this problem? We don't have this problem because of this. We are proceeding in a little bit different fashion. Instead of telling the computer to draw all the diagrams up to order alpha squared, put numbers on them, put them in a cross-section, and tell me the distribution associated with a particular observable, we do a different thing. We rearrange Feynman's series first, you see, before we do any calculation of anything. We go into the theory and rearrange it in such a way that all of the things causing him trouble are in these exponents. They're all exponentiated because they have the property that in that particular theory they do exponentiate. So we just pulled them all out of there from the beginning. And we're left with reasonably well-behaved residuals, these guys, betas, and they don't behave numerically in these wayward ways. They just don't have the singularities in them to behave in that way. They're just, now they're not simple functions, I don't want to say that, but the computer has no trouble to handle these. They just have no trouble to handle these. No semi-soft approximation is required, you see. And this is the difference between our approach and what the brute force automated, fully automated method of Cigna's program is. This is the main difference. When we go to all of these machines I showed you have the property that they want to run at higher energies. In the case of, and the normalization required for the region of acceptance required for the luminosity is a small angle region, you see. These are milliradians here. At the Z for the left, this was our acceptance. Now these machines, as you see, these numbers change. They're a little bit wider because they have more intense beams and also because of other reasons, except in the case of the IOC, of course, where even there it's also somewhat wider. The energies are different, I'm showing here. So we are, Z physics is what I just talked about, but FCCE can also go up to the top threshold, for example. I think that's as high, 350 GeV is as high as they intend to take it, and then they will switch over to the Big Hadron machine. Whereas the ILC starts out, as you see, we show the 500, and then of course we also have ILC 1 TeV. So you see, that's why I said it should be at the 500 to 1 TeV place in that original plot. And I think he did have it there at one version of the talk, but when the Japanese said they're not going to do it, he took it off. I think that's what happened. And then, of course, click, and as you see, they go out even further, and they can get up to 3 TeV. So the key point is the transfer over the value of the square of this number. And as you see, these numbers really control, because that's what the cross-section really depends on. And the T itself also enters in some parts of it because that determines the big logarithm. And as you can see, the T's are quite different as you go from FCCEE on the Z out to this 3 TeV machine the click that I discussed. But remarkably, you can see that these numbers are kind of all in the same ballpark. I mean, okay, this one, in other words, this T over S thing is the reason that we get, one way of saying it is that's the reason that we have such a good control over all of these things, even though the energies are very, very different. And so therefore we've done this analysis of these higher energy cases. We did it. For the 500 GeV IOC, which probably will not occur. One of the things you have to get used to as a theorist is what? Is calculating stuff that what? That will end up being useless because the opportunity for it to be used was just not chosen by nature. It's nothing wrong with your calculation. And in our case, the people making decisions are part of this nature. And they have decided to skip this. You know, they're just going to skip that, okay? They're just going to skip that. But had they not skipped it, you see, we could get very close to 1.6 to the minus 4. These are the same categories I had before. And we could get pretty close to what we have on the Z for the FCCE. But it's going to be skipped probably. I can't tell you how many things I've calculated. Just not used, you know. And so, but I enjoy the calculation. So what can okay, so they don't use it. If we look at the others, you see we went through and we did all of them. So we have the FCC 350, the IOC 1000, and the CLIC 3000. You go through, and they're all down in it except for CLIC, where we would probably need to do a little more work. We know how to make that 16 become a 1. Well, with support, we could make all of them become 1. But, you know, again, the one that looks most realistic is this FCC. CLIC is not done. If you ask at CERN, what is the status of CLIC? They say it's still an interesting thing to develop. It still has a potential to have some kind of major breakthrough where they could do it much more cheaply than what is being asked for now. And if somehow the foreign ministers do not approve this ambitious FCC-EE followed by FCC-H8, maybe they will go to that. So they don't, they want to be conservative. They don't want to play their cards, throw away a card that they might need. Let's put it that way. But they really want this one, is what they really want. So I'm kind of at the end. It's a little depressing because what DOE said is true. None of what I told you today is urgent. So therefore I have a very short summary. Need financial support for a big new project. That's my summary. Thank you for your attention. Any questions? Let me get the mic. Surely you must have some questions. Okay, you go right here. Let me just give you the mic.
Okay, thank you.
Yeah.
Now, if we put a number here for RHC, for the current the Super Collider, so what's the number? Is it 10 to the minus 3 or 10 to the minus?
For the LHC, it's a different question because the way they do their luminosity is with a different process. It's not with the same process. These colliders are all E plus E minus, and they use lowering or Bible scattering and all of the higher corrections of that to determine how many events they're counting. But at the LHC, they have a very different approach. They have even a machine physics method that they like the most. Ken can comment more coherently than I can. But they really, this machine physics method is, what is it now, 1 or 2%, I think they get for the luminosity error. 2% maybe or something like that, I forget what it is. But it's done with machine physics processes rather than with this lowering on Bible scatter. Ken, you want to add something?
I think I already said, but yeah, the luminosity measurement we can make at LHC is on the order of 2 to 3%, which is done by a few different methods.
So I have another quick question. When you talk about the neutrinos, you see the a neutrino about 2.99 something,
That's right.
which means actually we have only three species.
Three small mass neutrinos. It doesn't say that we don't have one of these heavier ones that the Z cannot decay to. So, for example, there's a lot of models out there with heavy neutrinos, and there would be their mass is too large for the Z to decay to it.
I see. Yeah. Any other questions?
So, are there any particular believable beyond the standard models that, such as what you just said, like heavy neutrinos, that you expect to see or hope to see in the new colliders at the LHC at CERN?
Yes, I would say yes. The answer to that is absolutely yes. In fact, I want to tell you, John Ellis has written a recent article that I didn't have a chance to take anything from it, unfortunately, so I'm sure there was something in there I could have put in this talk, but I didn't have a chance to do it. But you might even still see something at the LHC. They haven't been very lucky so far. However, you have to remember history. The accelerator in France, DM2 they call it, was E plus E minus, and it could go up to an energy of about 2.8 GeV, E plus E minus. It didn't see anything except the states that we already know from the naive quark model, the fire, the roll, things like that. That's all it saw. So everybody concluded that that's what the way nature is. However, Bert Richter at SLAC has managed to bootleg an E plus E minus collider. And when I say bootleg, what I mean is when Professor Panofsky, the director of SLAC, asked for DOE to support his idea to make an E plus E minus storage ring that could reach energies of about 5 GeV, DOE, based on what this DM2 had found, and with no other evidence of anything beyond the ordinary 3 quarks that people were beginning to accept, we don't need that. It's not urgent. So what did Richter do? The SLAC theorists, Professor Bjorkane and others, were adamant that this should be done because you don't know until you look. And so Professor Panofsky had the genius to believe that he should somehow find a way to get Richter the money to build that storage ring. So he took it out of the budget of the approved money for the 2-mile-long experiment, the so-called linear collider one. He just siphoned off from there because he had something called director's discretionary budget. Using that, he gave Richter the money on the side to bootleg construct the Spear storage ring. And what happened? They were able to look at 3.1 GeV, and they discovered the psi J resonance, that we have charm, and Bert Richter has been invited to Stockholm for the Nobel Prize. So just because so far they don't have anything, history tells you that you cannot assume they will finish with nothing. You won't know until they finish looking.
So there's only maybe a handful of good candidates you could still find at LHC, or?
We don't know we have some prejudices about models, and these models all said that the particles should be around, 1, 2 TeV. This is the prejudice. But maybe they're not there. Maybe they're just beyond that. We don't know that. You know, you don't know until you look. You just don't know until you look.
Thank you.
Another thing means so far now have we got any evidence so that we can say that the particles are not point like some
Say it again.
means is there any evidence till now so that we can get some hint about something that is beyond the point particle theory like the string theory or some models like that?
You mean that whether or not there's anything experimental that has been seen that would suggest that we need strings or something like a string? Yeah. Well, the answer to that is no, there isn't. There's plenty of theoretical arguments about why you might need a string. But if you're talking about experimental observations, no, we don't. We don't have that. In fact, I think that's one of the reasons, to my surprise, my friend, Professor Edward Whitten, who is, okay, you don't know my age, so I can say this. He is 3 years younger than I am, has retired his big professorship at Einstein's Institute for Advanced Study. And, of course, I was hoping that he wouldn't do that for a lot of reasons, not just because he's my friend. And, but he did it. And I think this what we talk about has entered into this decision because he told me in 1988, right after the string revolution when Green and Schwartz started, he told me, I was giving him and his wife a ride down from Salam's Institute to the place where we stayed, and he told me in that car that he thought he could solve string theory in 25 years. This is what he told me. And has he solved string theory? He has created something where they claim there are 10 to the 2,500 realizations that could all be the theory. Is that a solution? I'll leave it to you. I'll leave it to you. Any other questions? Well, we're a little bit past 5 and people have places to go. I really appreciate you coming to my talk. I realize that I can get a little bit carried away, but I realize I can.